In this video, we're going to look at the substitution method, which allows us to integrate more complicated functions where we've got a special case of a function and its derivative both included within an integral. First, we'll look at the theorem, which tells us that if we have, as I just stated, a function, in this case it's showing up as a composition function, and its derivative sitting right next to it within the integral, what we'll do is we'll make a substitution change so that we can have something that's more simplistic for us to integrate. First, let's look at a proof of this, and then we'll do a couple of examples. So let's start by assuming that capital F is the antiderivative of lowercase f. What we mean by that is that if I take the integral of lowercase f, I'll get capital F back. So then looking at the composition function, taking this function g of x and plugging into capital F, and then taking its derivative, that would be the same as looking at the derivative of the original function, the original composition function, and then we multiply by the derivative of what's on the inside. This is the chain rule that we learned about a while ago. Again, we take the derivative of the original function as we see it, and then we tack on the derivative of what's on the inside. Okay, and then using the substitution, the assumption that we made at the very beginning, we're saying that, well, if I take the derivative, looking at this part here, if I take the derivative of both sides of this, what I get is, let's see, d dx of the integral of f is going to be equal to taking the derivative of this side. In this case, the derivative and the integral, because they're opposite operations, they're going to cancel each other out. So I can say that the derivative of capital F is equal to lowercase f. So I'll make that substitution down here and say that this is lowercase f of g of x times the derivative of that inner function. So, putting these two ideas together, what we're saying is that capital F of g of x, the composition, is the antiderivative of f of g of x times g prime of x. Okay. Now what we're going to do is make that substitution that we talked about just a minute ago. The standard variable that we use for substitution is u. So we're going to say u is equal to that inner function g of x. So looking at this and this, I'm going to write the one on the right. I'm going to switch the sides of these. I'm going to take the integral of both sides of that. I'll write the integral, the one that's on the right-hand side first, f of g of x times the derivative of g is going to equal the integral of the left-hand side and similar to what we just did before, when we have an integral and a derivative next to each other, they're going to cancel each other out. So we could write this as capital F of g of x. And because we don't have any bounds on this integral, we'll put a constant of integration plus c there. And then using this substitution that we created, instead of writing g of x, we'll write u. So this is f of u. And then if we think about taking the integral of that, that would be the same as taking the integral but also having the derivative at the same time. Again, those two things will cancel each other out. If I take the integral of that and the derivative at the same time, that plus c is going to go away because the derivative of c is just going to be 0. And then using the substitution of capital F being the antiderivative, we can say that this is just lowercase f of u. What we've effectively done is made a variable substitution between what we started with, it looked very complex, and we changed it into something that's more simplistic, hopefully something that we know how to integrate using the techniques we have from before. Let's do a couple of examples to show how this works. In the middle of this slide here, we've got the process that we use, and I'll show you on these two examples here. So for the first example, we want to look at the function and we want to see if we can determine one function overall and then its derivative sitting there at the same time. Looking at this, if I let u be equal to x cubed plus x, then if I take the derivative, du dx, that would be 3x squared plus 1. And I see that sitting right here. So that's kind of the idea of what I'm looking for. What I'm going to do is I'm going to multiply both sides by dx. So I'm going to change this to be du equals 3x squared plus 1. And then I'll tack the dx onto the end. Let me make a little more space here. Move this down. Okay. So looking back at the original, I'm going to rewrite it. I'm going to rewrite it as this here is u to the 5th, and this whole part here, looking at what we have here, is du. So I think I've been able to substitute this to say u to the 5th du. And then I'll follow the process I know for integration. I'll increase the power by 1, so u to the 6th power, and then I divide by the new power, plus 6, and then I tack on the variable, the constant of integration. And then to finish this, I'll go back and resubstitute back into x terms from that original substitution I made. So the final answer will be x cubed plus x, all raised to the 6th power, divided by 6 plus c. All right, let's look at this second example. Let me make a little bit more room here. This one is a little different because as I look at it, I don't necessarily see the derivative sitting there like I did in the first one. So I've got the integral of, let's write it this way, 2x plus 1 to the 1/2 power dx. Well, in the example I did before, the item that was raised up to a power, that's what I did the substitution for. So maybe I'll try that same technique here. Let's let u equal 2x plus 1. If I take the derivative of both sides, I'll have that I get just 2. Multiplying both sides by dx, I have that du is equal to 2 times dx. Well, I've got dx sitting here, but not 2. But maybe I can use this technique where I make it look the way that I want to. What if I were to, let's say, put a 2 in here and then balance it out by putting a 1/2 on the outside? Those two things would multiply out to be 1, where I wouldn't change the overall impact on that integral. So I think what I'm going to say is that I have a 1/2 on the outside, the integral of u to the 1/2 power, and then this 2 dx, I'm going to call that du, because that's what we had here. I know how to integrate this. The 1/2 in front is just along for the ride. I'll raise the power up by 1 so that I'll go to 3/2, and then I divide by the new power, the 3/2, and then plus c. If I take that 3/2 and reciprocate it, I'm going to end up with u to the 3/2 over 3. And then I go back and resubstitute for the original substitution I made. So my final answer here will be 2x plus 1 to the 3/2 power over 3 plus c. These are both examples of indefinite integrals, but we can follow a similar process if we have a definite integral. The only thing that we have to take into consideration that's different here is that the bounds change when we make a change in the variable. So I'll do a couple of examples here. We've still got the same idea where we've got a composition function with its derivative sitting there, but notice that the bounds change because of the substitution rule that we're using. All right, looking at the example on the left, I'm going to let u be the x cubed plus 1, because when I take the derivative, the power will drop down by 1, and that looks like that other component that I have sitting in the integral there. Okay, so rearranging this, du is equal to 3x squared dx. This part and this part together is du. So I can rewrite this integral to be, I'm going to write this as x equals -1, x equals 1, and I have u to the 1/2 power du. The reason that I wrote x equals is because I haven't made the variable substitution yet in the bounds, the upper and lower bound. The original integral was written in terms of x, and so those lower and upper bounds are in terms of x. To make a change in the bounds, we're going to use the original substitution that we had back up here. So when x is equal to 1, what do we get for u? U is going to be 1 cubed plus 1. We're going to get 2 there. When x is equal to -1, we'll have -1 cubed plus 1. That's equal to 0. So to rewrite this whole integral in terms of u, I also need to change the bounds to be in terms of that variable as well. So my new integral is going to be, the lower bound is going to be 0, the upper bound is going to be 2, and then I have u to the 1/2 power du. Okay, so this will be u to the 3/2 over 3/2, evaluated between 0 and 2, or let's write it as 2/3. I'm going to go down so I have more room there. 2/3 u to the 3/2. So we plug in the upper bound first. So we'll have 2 to the 3/2 minus 0 to the 3/2. 2 to the 3/2, I think that's the square root of 8. I think this is 2 times the square root of 8 over 3. Or, yeah, that would be 4 root 2 over 3. This is our final answer. Because we are looking at a definite integral here where we're trying to find a particular number, we don't have to worry about changing back into the original variable x like we did in the examples before where we had an indefinite integral. We just want to make sure that we change the bounds to match the new variable we're considering. All right, let's look at this second example where we're looking at the integral between pi over 4 and pi over 2 of cotangent theta times cosecant squared theta. I want to pick one of the variables to be the main substitution variable u, and then the other one is going to be the derivative or something close to the derivative. So if I let u equal cotangent of theta, then when I take the derivative of both sides, du d theta, I'll get negative cosecant squared theta, or du is equal to negative cosecant squared theta d theta. Looking at the original integral, I almost have that. I'm just off by a negative sign. So if I add a negative sign in here and then balance it out with another negative sign on the outside, then this whole part I can say is du, and then this part here is equal to u. I also need to make sure that I change the bounds. So when theta is equal to pi over 4, what do we get for u? Again, we're going back up to the original substitution that we created, and we're plugging pi over 4 into that. The cotangent of pi over 4 is going to be 1. And then when theta is equal to pi over 2, this should be an arrow, then u is equal to 0. Okay, so rewriting this original integral, I'm going to say I have that negative out in front. The bounds are changing from 1 to 0. Notice that this is the lower bound and this is the upper bound. Even though they're in reverse order, we've got to follow what we have plugged in there. And then we'll have u du. All right, well, if I integrate u, I'm going to get u squared over 2. That negative sign stays out in front, and I'm going to evaluate between 1 and 0. So I'll plug 0 in first. Negative 0 squared over 2, just 0, minus a negative 1 squared over 2. So I think overall, for this integral, I'm going to get 1/2 as my answer. We've now learned enough techniques to tackle some new definitions or ideas that of integrals that we can add to the list of ones that we'll be using. And these are integrals of some of our trig functions. I'm going to show you how to prove this one right here. And the proof involves substitution, so that's why we haven't really looked at these up until now. We talked about derivatives, but not integrals. So let's start with the integral of secant x dx. And I'm going to rewrite it in a fancy way by multiplying it by this complicated looking fraction. I'm just taking and multiplying by a form of 1. So it's not changing the function overall, even though it looks like I've really added something in there that's complicated. Multiplying that secant x through the numerator, I'll have secant squared plus secant tangent. And then that's all divided by secant plus tangent. Okay. Now we're going to use that substitution method. I'm going to let u be equal to secant x plus tangent x, what I see down in the denominator right here. When I take the derivative of that, du dx, the derivative of secant is secant times tangent, and then the derivative of tangent is secant squared. So looking at the numerator, they're written in the reverse order, but I can see that this, with this, if I took the dx and put it over here, that numerator and the dx on the other side, that's equal to du. That's pretty convenient, right? So we can say that instead that this is du over u. Or the integral of u to the negative first power du. We know that that is the natural log when we've got something in the denominator like that. So integrating this, we're going to get the natural log, absolute value of u plus c. And then again, we'll go back to that original substitution we made up here. And our final answer will be the natural log of absolute value secant x plus tangent x plus c. So that's just a simple proof using substitution to show one of these identities that we have. All right, thanks for watching. The next video will go through calculating area between two curves. I'll see you in class.